गुड आफ्टरनून एवरीबॉडी। और ये आज बहुत दिनों के बाद आज ऑनलाइन क्लास ले रहा हूँ। और ये आज का क्लास जो है इनर प्रोडक्ट स्पेस, ये बस मेरा एक यूट्यूब फैन पी मुकुल उसका रिक्वेस्ट पर मैं ये क्लास ले रहा हूँ। अदरवाइज मेरा ये क्लास में ऑलरेडी ऑफलाइन मेरा कॉलेज स्टूडेंट के लिए कंप्लीट कर चुका था। बस पी मुकुल उसके कहने पर मैं ये क्लास कर रहा हूँ। पी मुकुल एक दिल्ली यूनिवर्सिटी का एक स्टूडेंट है, दिल्ली यूनिवर्सिटी का एक स्टूडेंट है, बीएससी स्टूडेंट। ओके, उसके कहने पर मैं बस और 2-3 क्लास ले लूँगा उसके लिए और आपके लिए भी। ओके, लेट अस स्टार्ट। What is an inner product space? Let's come to its definition. So, what is an inner product space? Let V be a vector space. Let V be a vector space over a field F, and that field F may be the set of real number or the set of complex number. Okay, V be an inner product space over a field F, then V be a vector space over a field F, then an inner product, then an inner product on V is a function, then an inner product on V is a function that assigns every order pair of vectors x comma y belongs to V to a scalar C in F. Okay, so what is an inner product? An inner product on a vector space V is a function that assigns every order pair of vectors x comma y belongs to V to a scalar C in F, and it is denoted by this symbol in this bracket, this x comma y. And what you say here, the inner product, suppose V is a vector space, and what is an inner product? This is a function, you can say this is a function f from V cross V to F. That means in its domain this is V cross V, that means you have to take two vectors x and y belongs to V, that means x is from V and y is from V, and what you will get if you will take two elements from V, then the resultant is the result is a scalar, that is C, and this is this one. This is a constant C, or this is a scalar C. Okay, this is just your inner product. Now comes to its properties. Also, in some book, we also see the notation is also like this. In bracket x comma y you can write, or otherwise you can write this is x dot y, like your dot product. So this is also a notation of inner product space. So now comes to its properties. Okay, the first property, let x comma y comma z belongs to this vector space V, and C belongs to field F. That means C is a scalar. Now, what are the properties? I will write four properties. Then inner product of x plus y comma z is equal to x comma z inner product plus y comma z inner product, like a distributive property. And in the second one, then c x comma y inner product, c is from field F, which is a scalar, so we can take c outside of this bracket. So I can write this is c times inner product of x comma y. Then the third property, this is x comma y inner products conjugate. This is the bar of x, inner product of x comma y bar. This is your y comma x, and this bar denotes the complex conjugation. We can say where the bar denotes complex conjugation. Okay. Then the last property, inner product of inner product of a same vector with itself. Means inner product of a vector with itself. This thing is always greater than 0 for all x, and this inner product is equal to 0 if and only if x is equal to 0. That means if a vector is 0, then its inner product with itself is equal to 0, and x comma x inner product is greater than 0 for x not equal to 0. For x not equal to 0. So in general, we can write this thing as inner product of x comma x is greater than equal to 0 for all x. That means for x equal to 0, their inner product with itself is equal to 0, and for x not equal to 0, its inner product with itself is strictly greater than 0. Okay, these are the four properties related to this inner product space. Okay. Related to this inner product. Now, what is the inner product space? So, what is an inner product space? Inner product space. A vector space V, a vector space V together with an inner product, together with an inner product is called an inner product space. Is called an inner product space. That is this is a this is V, and this is the inner product. We can symbolically denote this way. So this is V together with an inner product, and this is called an inner product space. Okay. So, and in the definition of inner product, I already told you that field F may be the set of real number, or this is a set of complex number. So if the field F is a set of real number, that means a vector space is the inner product space over the field R. This is called an Euclidean space. This is an Euclidean space, and a vector space over the field C. This is called an unitary space. Okay. Now comes to a theorem. Let V be an inner product space. Let V be an inner product space. Let V be an inner product space. U, V, comma W be any three vectors in V. So U, V, W belongs to V, any three vectors in V, and alpha be any scalar, and alpha be any scalar, then we have to show these things. What are these? U, comma V plus W is equal to U, comma V inner product plus U, comma W inner product. Similarly, in second bit, I have to show U, comma alpha V inner product is equal to alpha bar U, comma V inner product. And in third bit, we have to show 0, comma U inner product is equal to 0 equal to U, comma 0 inner product. That means inner product of 0, comma U or inner product of U, comma 0, all these things are 0. That means if in an inner product, if one vector is 0, then its result vector is 0. That means 0 into any vector's inner product is 0. Now we'll prove this one. Consider inner product of U, comma V plus W. Okay. So in the properties we already know this thing. So in the above properties, like here, we know this one. X inner product of xy conjugate is equal to y, comma x. That means if we will change their order, that means I have written here first x, then y, and here I have written first y, then x. So if we will interchange their order, then there will be a conjugation. Okay. So if I will change here the order, then there will be a conjugation. That means we can write it as V plus W, comma U inner product. Then a conjugation will be here, or a bar will be here. So now for this one we can write this is V, comma U inner product plus W, comma U inner product. Then this whole bar is here, and I have written this is for inner product of V plus W, comma U is this one, and bar is like previous one. So I can write this one as we already know these things, like Z1 is a complex number, Z2 is another complex number, then Z1 plus Z2 whole bar is your Z1 bar plus Z2 bar. So by using that property, I can also write for this one. This is V, comma U conjugate plus W, comma U conjugate. So if I will remove the conjugate, then I will interchange the variables or interchange the vectors. So I can write this one as U, comma V, and for second one this is U, comma W. This one what we want to prove this. Okay, this is proved now. Now come to second bit. U, comma alpha V. So in the similar way we can also prove this one. U, comma alpha V. This one is your alpha V, comma U conjugate. Since I interchange the order, that's why I have to give the conjugate. So what can I write for this one? Conjugate of alpha V, comma U. So the inner product of alpha V, comma U is conjugate, and this one conjugate will be here. And what is the inner product of alpha v comma u. This is alpha times v comma u. And the whole conjugate is there. So also like we know already z1 into z2 bar, sorry, z2 conjugate is your z1 conjugate into z2 conjugate, or you can say alpha into z1 bar is equal to alpha bar into z1 bar. So for this one I can write this one is alpha bar whole into v comma u inner product conjugate, and we can add this one as alpha bar whole into v comma u conjugate is your u comma v. Okay, this is now proof. This is alpha comma u v is equal to alpha comma u v conjugate. This is your u comma alpha v is equal to alpha bar u v. And previously you already know this thing, alpha times u comma v conjugate is your alpha times u comma v inner product equal to alpha times u v inner product. So if alpha is coming from the first vector, then it will be like alpha, and here what you are getting, if alpha is coming from second component or from the second vector, then alpha will be alpha bar. Okay, this is the difference. So now come to the third property. So 0 times 0 u conjugate 0 u inner product, we can add this thing as in place of 0 we can add this is 0 times v u, because 0 times v is 0. So now this is in this form 0 times v comma u. So we can take 0 outside, like this property in place of alpha, 0 is here, so we can take 0 outside of this inner product. So this will be 0 times v comma u, and we know 0 times anything will be 0. So 0 u's inner product is 0. Similarly we can write u comma 0's inner product will be also 0 similarly. Okay, in place of u we can write 0 into v, then you can take 0 outside of this inner product, then the result will be 0. Okay, now some special type of inner products, some special types of inner products. So what are some special types means? Special types means if the vector space is something different than how the inner product is defined. Like in the first case, if I will take my V is, that means my vector space is the nth tuple real number. This is the nth tuple real number. So if my vector space is a nth tuple real number, so let xy belongs to V. So how my xy will be looks like? My x will be from Vn, that means your x1, x2 like xn. Similarly, y is from Vn, so y will also looks like y1, y2 like yn. Then what will be the inner product of xy if xy is from vector Vn? So this inner product is x1, y1, x2, y2, whatever you know previously, this is the inner dot product of xy. If your x vector is x1, x2, dot dot up to xn, and your y vector is y1, y2 up to yn, then inner product of xy is nothing but your the dot product of xy This is the component wise product. X1 into Y1 plus X2 into Y2 plus X3 into Y3, like this up to Xn into Yn. And similarly, if V is your VNC, that means your nth tuple complex number. Nth tuple complex number, then so if xy belongs to V, similarly we can write for x, this is x1, x2 like xn, and for y this is y1, y2 dot dot yn, and all these x1, x2, xn and y1, y2, yn are complex numbers. Okay, since these are nth tuple of complex number, this V is. So what will be the inner product of xy when xy belongs to nth tuple of complex number? Then their inner product is x1 y1 bar plus x2 y2 bar, then x3 y3 bar plus dot 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 like your xn yn bar. Okay. So this is the inner product space on this type of vector space. Similarly, if I will again if I will change my vector space, inner product of UV, where U and V are row vectors, is to U and V are row vectors, then what will be the inner product of UV? This is UV transpose. Okay. Similarly, inner product of UV, this will be U transpose V if this U and V are column vectors. So if U and V are column vectors, then their inner product is U transpose V. Similarly, if U and V are row vectors, then their dot product is U V transpose. Okay. Also, the another types. Suppose my vector space is script C01. That means in the vector space, what are the what is your script C01? Script C01 is your the set of all continuous functions, the set of all continuous functions defined on close 01. Script C01 means the set of all continuous functions defined on close 01. So if V is a vector space like this, your script C01, and F, G are any two vectors from this V or from this script C01, then what will be the inner product of Fg? This is your integration from 0 to 1 f of t gt dt. Okay, this is the inner product of f and g, where the vector space is script C01. That is the set of all real valued continuous, the set of all real valued continuous functions defined and close 01. Similarly, if my V will be script C01 and I am giving here a subscript C, that stands for complex number. That means here the vector is the set of all complex value, the set of all complex value continuous functions defined on 01, closed 01, defined on closed 01, and Fg belongs to V on this V, then what will be the inner product of Fg? This will be integration from 0 to 1. This is your f of t into g of t conjugate, then dt. Okay. So now we studied here 5 types of definiteness of inner product if the V, that means the vector space, is different. Okay. Then comes to now the inner product or inner product related to inner product space. These things are completed. Now comes to what is a norm. Okay. So what do we know by norm? Let V be a inner product space. Let V be an inner product space. Let V be an inner product space. Then for each u belongs to V, u comma u, that is the inner product of u with itself, is a non-negative number. This is a non-negative real number, we can say. This is a non-negative real number irrespective, non-negative real number irrespective of whether V is over the field of real number, over the field of real number or complex number. That means whatever the field, whether it is a field of real number or it is a field of complex number, whatever the field, that does not matter. You can say the inner product of u with itself is always a non-negative real number. So what happens if this thing is always a non-negative real number, then the square root of this u, positive square root of this u comma u, this is your norm u. Okay, because since this is a non-negative number, and if I will take its positive square root, then it will be a non-zero. It will be a non-zero number, and this is the definiteness of norm u. So that means norm of u, that is nothing but this is the positive square root of inner product of u with itself. And from this definiteness, since we know u comma u, this is a non-negative number. Non-negative means u comma u's inner product is always greater than equal to 0. That means non-negative means it is not negative, but it may be 0. So it is always greater than equal to 0. So if you will take its square root, that means u comma u square root, positive square root, this will be always greater than equal to 0. So norm of u is always greater than equal to 0, and norm of u equal to this one. This is the positive square root of u comma u. Okay, this is the definition of norm. So I can take one or two examples. So if your x is equal to x1, x2, like your xn, then what will be the norm x? You know, norm x is the inner product of x comma x. So what will be the inner product of x comma x? So whether this thing belongs to a real n tuple or complex n tuple, whatever it may be. So the resultant will be x1 square, x2 square, x1 mod square, x2 mod square, x3 mod square, like that up to xn mod square whole root over. So this is the mod x. Similarly, if I will take another example, like f is a function that thing belongs to script c 01. Whether it is script c01, this is over the set of all real valued continuous function or the set of all complex valued continuous function, whatever it may be. We can say this thing script c 01 over c, that stands for complex number. So if f belongs to this thing, then what will be the norm f? In the same way it will be defined. We know enough norm of x is the square root of this one. Okay, and we know what is the inner product of f with itself. This will be integration from 0 to 1, and f of like this one, in place of g of t you have to put f of t, because this is the inner product of fg, and we want to find what is the inner product of f comma f. So this will be f of t into f of t bar. So we know z into z bar, this is your mod z square. We know this property. So what I will use or what I will get if I will replace g by f. So this will be your f of t into f of t bar dt, and whole to the power half, because I am taking the square root. Okay, so what will be of this one? This is from 0 to 1, and f of t into f of t bar, this is your f of t mod square. So integration from 0 to 1 f of t mod square whole to the power half. Okay, so this is your norm f. So what we note here, or what we can note down, so in other words we can say, in other words we can say norm of a vector is nothing but the magnitude of a norm of a vector u is nothing but the magnitude or length of vector u. So norm of u means that is the length of u, length of vector u. If u is a vector like this one, if u is a vector and norm of u is nothing, this is the length of u, or which is your norm u or mod u. Okay, so this is the definition of norm. Now comes to some theorem related to norm. Now comes to the first theorem. Let V be an inner product space. Let V be but let V be an inner product space, then for any arbitrary vector u v in V, then for any u comma v, sorry, then for any u comma v belongs to V and alpha be any scalar, and alpha be any scalar, then we will show that norm of alpha u equal to mod alpha norm u. Alpha is a scalar. Okay. The second point, if norm of u is greater than equal to 0 and norm of u is greater than equal to 0 and norm of u is equal to 0 if and only if u is equal to 0. Okay, so in third point, what we have to show, this is the inner product of u v modulus. This is the modulus of inner product u v, and this thing on inner product of u v can be written as this is u v dot product its modulus, or we can say modulus means your norm. Okay, modulus norm means its modulus. Since there is a vector u, if u is a vector, then norm of u is nothing but this is the length of u. So mod of inner product of u v, that thing you can write this one. This is norm of the inner product of u v can be written as u dot v and its modulus, and this is nothing, this is just u v inner products norm. Okay, since u dot v, this is a vector, scalar, whatever it may be, modulus is norm is just its length. So this thing can be written as this. All these things are similar, and we have to say this norm of u dot v or norm or this mod of inner product u v. This thing is less than equal to. This thing is less than equal to norm of u dot norm of v, norm of u into norm of v, because norm of u, this is a scalar, this is a scalar, this dot you can say this is a product, and this inequality is just squashed inequality SCH WA RTJ or RJ squash inequality. And another one is triangle inequality, that is the norm of u plus v. This thing is less than equal to norm u plus norm v. So now comes to its proof. First one, alpha u norm. Consider alpha u norm square, and we know what we know. Norm u is the square root of u comma u inner product. First is square root of u comma u inner product. So what will be your alpha u norm square? So if you will take the square of both sides, then your norm u square is your u comma u inner product. Okay. So norm of alpha u square, this is your inner, this is the inner product of alpha u comma alpha u. So we can take this alpha outside, this alpha, and if this alpha will go to outside, this will be alpha bar, because this alpha is from second component or from second vector. So this thing, if we will go outside of this inner product, this there will be alpha bar. So this is alpha into alpha bar, then u comma u inner product, and z into z bar, this is your mod z square. So I will write for this one, this is mod alpha square, and then u inner product, this is your norm u square. So what I got, if this thing will continue, then this is alpha u norm square is this one. So if I will take the square root of both sides, so alpha u norm will be your mod alpha norm u. Okay, this one. So now comes to second one. Norm u. What is your norm u? Norm u is the inner product of u comma u square root, and since we know inner product of u with itself is always, inner product of any two vector is always a non-negative real number. From the definition we already told you, norm since u comma u is always greater than equal to 0, so its square root is always greater than 0, and its square root is nothing but this is your norm u. Okay, so this thing you have to write. So norm u means this is the square root of u comma u, and this thing is always greater than 0, since u comma u inner product is a non-negative real number. Since this is a non-negative real number, its positive square root, this thing will be also a non-negative real number. Non-negative real number means greater than equal to 0, that is not negative, non-negative, that means it will be either positive or 0. Okay, so this thing is okay. And here also it is given if norm u equal to 0. And what do we mean by norm u? Norm u means this one, this is the inner product of u comma u square, first square root of this one, this thing equal to 0. And we know square root of any number equal to 0 means that number should be 0. That means square root of 0 is only 0. So this thing must be 0. And inner product of a vector with itself is equal to 0 means that vector is 0. That means 0 vector. Okay. So now comes to third one. So in the third one, the sparse inequality. So how I will prove this sparse inequality? So in sparse inequality, if u, now we are proving this sparse inequality. So if u equal to 0, the statement is obvious. The statement is obvious. See the statement first. That is inner product of u comma v is less than this one. If u is equal to 0, that means inner product of u v will be 0. Similarly, since u 0, norm u will be 0, so the 0 into this one will be 0. So at that time equality holds. That means if u is equal to 0, statement is obvious means what? U comma v inner product will be 0 and 0 modulus will be 0. Similarly, on the right hand side, norm u into norm v is there. So norm u will be 0. So 0 into norm v, this will be 0. So left hand side will be 0 and right hand side will be 0. So at that time equality holds. If u is equal to 0, at that time the equality of the sparse inequality holds. So this thing is obvious. So if u is not equal to 0, we have to prove this thing. If u is not equal to 0, then consider w is equal to v minus alpha u, where alpha is equal to inner product of v comma u divided by norm u square. Okay. So if u not equal to 0, now consider another vector v, let it be, sorry, another vector w, let it be v minus alpha u, where alpha equal to this one. Then if we will consider this norm w square, and always this thing will be first step greater than equal to 0. In norm of any vector is always greater than equal to 0. So if I will consider this norm w square, this thing is always greater than equal to 0. And what will be a norm w square? This is w comma w inner product. And in place of w, I am assuming w as v minus alpha u. So this is v minus alpha u comma v minus alpha u. Okay. So like a distributive property, I can name this thing as v comma v minus alpha u minus alpha u comma v minus alpha u. Similarly, also I can simplify this one as this is v comma v inner product minus v for this one, okay, v comma alpha u. Similarly, for these two things, that means like first I have applied the distribution from left, and thus in this line I am applying distribution from right. So this will be, I can say this is alpha u comma v, then here minus and here is also another minus, so this will be plus alpha u comma alpha u. Okay, these are all the distribution properties. So inner product of v comma v, this is your norm v square. Similarly, v comma alpha u, here we can take alpha outside of this inner product, and this will be, since alpha is from this second vector or from the last vector or from the second component, then conjugate will be there. So this will be alpha bar v comma u inner product minus alpha times, this is u comma v inner product, and here alpha, and here alpha bar. Okay, so this is u comma u inner product, and this is your norm v square, and this is say here alpha is this one, so what will be your alpha bar, and norm u square is a constant. Constant means this is a real number. So what will be the alpha bar? If your alpha is this one, then alpha bar will be, this is your v comma u conjugate divided by norm u square into v comma u inner product minus, and alpha is here, alpha is your v comma u inner product divided by norm u square into u v. But you can interchange here the u v, we can write v comma u by giving its conjugate. Okay, so in place of u v I can write this is v comma u by taking its conjugate. Okay, and then here alpha bar, which is your mod alpha square, z into z bar, this is your mod z square, so mod alpha square, and u inner product with u, this is your norm u square. Okay, so what we will get here, this is your norm v square, and this is v comma u inner products conjugate with v comma u. So that is like z into z bar, which is your mod z, so I can write this one as your v comma u mod. Okay, just like z bar, this is your mod z square. Okay, v comma u inner product mod square divided by mod u square, sorry, norm u square minus, here is also v minus v comma u inner product and v comma u inner product mod, sorry, inner products conjugate. So I can also write in the same way v comma u mod square. So I am using this property z into z bar, this is your mod z square. Okay, so this one divided by norm u square, and here alpha, see here alpha is your this one, so what will be mod alpha square? This will be the mod of v comma u inner product square divided by, similarly norm u square was there, so norm u 4, this square is here, and here norm u square, so this is norm u square, this is norm u 4. So in this step I will cancel out here, so if I will cancel, then what will be this one? Only this thing will left. Okay, just I am omitting one step here. So what I will write here, this is norm v square, and this one, and this one, these two terms can cancel out, so I will write only this thing, norm v square minus inner product of norm v comma u mod square divided by norm u square, and this thing, this is your norm w square, and this thing is positive, that means this thing is greater than equal to 0. That means if I will continue that from the first step, 0 is less than equal to this one. So if I will take this one to right hand side, so what I will write, norm v square, or if you will take this one to the left hand side, what I will write, this is the inner product of v comma u mod square divided by norm u square. This thing is less than norm v square. So you can take this one to right hand side. So this will be v comma u inner product mod square. This thing is less than norm v square into norm u square. So now if I will take the square root of both sides, what I will get? Then mod of v comma u is less than equal to norm of v into norm of u. Norm of v into norm of u. And this is the Sparse inequality. Okay. SCHWARTZ, Sparse inequality. Okay. Now we'll go to the next triangle inequality. Consider u plus v norm square. So which is your u plus v inner product. Because we know norm u square is the inner product of u with itself. So I will write this thing like a distributive way. So u inner product of u with u plus v comma u plus v inner product. I can distribute it from right, u comma u inner product, u comma v inner product plus v comma u inner product plus v comma v inner product. Then u comma u inner product, this is your norm u square, and this is u comma v, and this is v comma u. So we can add this is u comma v inner product plus, and in place of v comma u we can interchange its position by giving a conjugate sign here. Then this is your norm v square, and we know z plus z bar, this is your 2 times real z. So I can replace here, this is your norm u square, and this is u comma v inner product, and this is u comma v inner products conjugate. So I can write this is 2 times real of u comma v inner product plus norm v square. And also we know if your z, like this is z is a complex number, like this is your x plus iy, and what is your real z? Real z is your x. So we know real z, this thing is always less than mod z. What is your mod z? This is the square root of x square plus y square root over. This is the first square root of x square plus y square. So we always know that real z is always less than mod z. So I will use that concept. So this will be less than norm u square plus 2 times, in place of real of this thing I will write real of this thing, in place of I will write less than equal to, less than symbol I have already given here. This is mod z. So mod z means this is mod of u comma v inner product, okay, plus norm v square. So, and we know in the last inequality, the Sparse inequality, I already know this thing. This is not less than equal to symbol is here, and this is norm u square plus 2 times, in place of this one. We just see what is the Sparse inequality. This one is the Sparse inequality, okay, in place of mod of inner product uv, you can write this thing is less than equal to norm u norm v, or norm v norm u. So less than equal to symbol is here, and in place of this thing I will write norm u norm v, then norm v square. Now this is norm u square plus 2 times norm v plus norm v square, which is here. This is norm u plus norm v whole square. The pen is not working. This whole square. So what we got here? Norm of u plus v whole square. This thing is less than equal to so this thing is less than equal to norm u plus norm v whole square. So if you will take the square root of both sides, what you will get? Norm of u plus v is less than equal to norm u plus norm v. Okay, this is the triangle inequality. This is proved. Okay, today is only this much. Thank you.